In this video, we're going to look at the first of two examples of how to make Bode plots. So here we see we want to make Bode plots for the transfer function shown below. So we have h of j omega equals 200 j omega divided by, and then in the denominator we have quantity of j omega plus 2 times the quantity of j omega plus 10. So the first thing that we note is that none of these terms in this equation look quite like what we saw in our previous videos identifying the 7 possible terms that we can see. So the first thing that we want to do is we want to get this sort of in the standard form. So let's put this in our standard form so that we can sort of use our sort of cheat sheet of what each of our 7 items does, and then we're going to make a Bode plot for each item. And then we're going to come and we're going to combine all of these together to create our Bode plots for this transfer function h of j omega. Okay, so if we want to get this in standard form, the main thing we want to adjust is this denominator. So when we had our poles, we had 1 plus j times something. So for the first term, what we can do is we can factor out a 2 to make that a 1. And then if we factored out a 2, we now have omega divided by 2. So we get something that looks like that. So again, we've just factored out that 2. So we want to do something similar with our second term in the denominator there. Here we want to factor out a 10 in order to make that a 1 plus j. And now because we factored out a 10, that omega becomes omega divided by 10. And we've not done anything with our numerator because that looks good. We have a constant and a 0 at the origin. But what we're going to see is now this constant is going to be updated because this 2 and 10 we factored out are going to need to be factored into that constant term. So we have 200 divided by quantity of 2 times 10. So our constant is going to become 10. We still have that j omega term. And now we have 1 plus j times omega over 2 times 1 plus j omega over 10. So now we've got everything in a form that looks familiar. We can see that we have, let's label some of these things. So here we have our constant. Here we have a 0 at the origin. And then in the bottom, we have 2 simple poles. And so we see the 2 simple poles have 2 different corner frequencies. But now we have this in the form of what we saw for our 7 items that can compose our transfer functions. And so we see we're going to be dealing with 3 of those items. So what we want to do is we want to look at each of those items individually, and then at the end we're going to combine them into a single Bode plot. And so remember, our Bode plot is going to consist of 2 things: magnitude and phase information, or gain and phase information. So let's look at each of these terms we have in this transfer function. The first is our constant, and in this case we have k equals to 10. So our gain, remember, is going to be 20 log of 10. So let's just say gain in decibels is equal to 20 log of 10. So log of 10 is 1, so we get 20 for our gain. And so remember, for our constant, we have just a constant phase of 0 or 180, depending on whether it's positive or negative. In this case, it's positive, so our phase is 0. So this is the magnitude in dB. And for our constant, it's just going to be 20. And as we saw for our constant, it has no frequency dependence. So we just have something that looks like this. Now for our phase, we said that we're just going to have a 0 phase. Let's make this a little bigger so it's easier to see here. So we just have 0 phase, and that has no frequency dependence either, so 0 degrees phase. Okay, so that was the easiest one to deal with. Now let's move on to this 0 at the origin. So let's say 2 is our 0 at the origin. So that's the j omega term in the numerator. And so let's draw our two components of our Bode plots. We're going to have our gain, so magnitude of h in dB as a function of omega, and we're going to have our phase plotted versus omega. And so for our 0 at the origin, remember the phase was just a constant 90 degrees. So we're just going to put constant 90 degrees, no frequency dependence for that. And for our magnitude, our gain, we have sort of these three key points. We have 0, 0.1, 1, and 10. And so we said that we have a 20 dB slope, 20 dB per decade. So at 1, we have a value of 0. And then as we go 1 decade to the left, we've gone down 20. As we go 1 decade to the right, we've gone up 20. So we get something that looks like this. And so again, that's a 20 dB per decade slope. Okay, so now the last thing we want to address is our two simple poles. So let's look at one at a time, of course. So we have 3 is our simple pole. And let's look first at the one that's 1 plus j omega divided by 2. And so what we can see from that is our corner frequency, our break frequency, our 3 dB frequency, however you want to call it, is going to be omega equals 2. So if we then come here, we're going to draw our magnitude and phase plots. So here we have magnitude of h in dB plotted versus frequency, and we're also going to plot our phase versus frequency as well. So our magnitude, remember we said we do this sort of linear approximation, and our corner frequency is sort of the frequency of interest where that's going to change. So let me make this a little heavier. So what we do is we have 0 until the point where we get to our corner frequency, at which point for a simple pole we begin decreasing at negative 20 dB per decade. So here we have negative 20 dB per decade, which is sort of kicking in at the corner frequency. So now for our phase information, we said sort of the key phase angles are negative 45 and negative 90 degrees for a simple pole. And the key frequencies are going to be 2 and then 1 decade to either side. So 0.2 and 20 in this case. So I've just multiplied and divided by 10. And so using again a linear approximation here, what we said is it's 0 if we're less than 1/10 of our corner frequency, and it's 90 if we're greater than 10 times our corner frequency. And at our corner frequency, our phase angle is 45, and then we just do a linear approximation in between. So I've drawn that kind of poorly, but that should be a linear approximation, a linear line with negative 45 degrees per decade slope. Okay, so of course our behavior for our other simple pole is going to be exactly the same. So let's go ahead and just copy this, and that way we can adjust without having to redraw everything. So not quite ready to paste yet, but let's do, so now we're going to look at the fourth component from our transfer function, which was our second simple pole. And so this simple pole was the one that was 1 plus j times omega divided by 10. And so that means we have our corner frequency, our break frequency, our 3 dB frequency. Again, we can call that by several different names, is that omega equals 10. So again, we have, of course, we expect to see the same general shape of this. The only difference is now we have a new corner frequency. So I'm going to get rid of these frequency markers here, and I'm going to replace them with our corner frequency, which is 10 for this gain plot. And for our phase plot, we have 10 is the corner frequency where the phase is negative 45. 1 decade lower is 1. So that's where we're saying below that we have a 0 degrees phase. And then 100 is 1 decade above. So above 100, we have a negative 90 degree phase. Okay, so now what we want to do is we want to add all of these terms graphically. So add all terms graphically, and what that's going to give us is our overall Bode plot. So as we come up through here, what we can see is going to be useful is to mark some of these key frequencies. So for instance, we see that our constant and our zero at the origin are sort of giving us the same sort of response regardless of our frequency. So we don't really have any frequencies where things are changing. But for our simple poles, we see some important frequencies here are 2, 0.2, 20, and then for our other simple pole, 10, 1, and 100. So let's go ahead and sort of draw out sort of our plot axes here. Okay, so this is going to be our magnitude in decibels versus our frequencies. So some of our key frequencies, let's say that we have, let's say that we have 0.1, and then 1 decade above that, we have 1 decade above that, we have 10, and then 1 decade above that, we have 100. So remember, this is going to be a semi-log plot, so this frequency axis is on a log scale. So those would be the key frequencies related to our simple pole with the corner frequency of 10. So now let's go to, and so that also is going to help us incorporate the introduction of the zero at the origin. So now let's look at the key frequencies for our simple pole with corner frequency 2. So we're going to add in some points here. So we're going to have maybe around here we have 0.2, around here we have 2, here we have 20, and here we have 200. And so again, if you wanted to be really accurate, you could write this on a semi-log graph paper. So let's go ahead and sort of copy this so that I have the same scale for my frequency and my phase. So let's see if we can't line that up. Okay, so hopefully that's more or less close. And then for the phase, we're going to again be considering that same information, but we're going to be dealing with negative and positive. So let me just adjust that a little bit. So we have something more like this. So this is going to be our phase information. Some key sort of degrees here are going to be our 45, 90, negative 45, and negative 90. So let's go ahead and label those, and we'll see how that comes into play as we get there. Okay, so this can be a little tricky at first, but basically what we want to do is we want to consider the contributions of all of these 4 components. So let's start by ignoring the phase and let's just focus on our magnitude or our gains. So for the first one, our constant, we see it's always contributing this 20, this constant 20. Our zero at the origin, we see it is contributing this constant 20 dB per decade. And then for our simple poles, we see they're not contributing anything until 2 and 10 respectively. So for everything below 2, we're just going to focus on these 2 items here. And so what we can see is at 0.1, we're going to be at 0. The reason I can say that is because we get 20 from our constant and negative 20 from our zero at the origin. So let's go ahead and add that point. So we know down here for our magnitude, we know we're going to be at 0 here, okay? And so then we see, well, we just have this constant 20, but we keep increasing 20 dB per decade for the zero at the origin. So at 1, we're now going to be at 20 from our constant plus 0, so we're going to be at 20 when we reach 1. Okay, so by the time we get over here to 1, we're going to be at 20. So let's say this point is 20. And so we then continue to increase. We keep adding more and more sort of slope there, but as we get a little past 1, as we reach 2, we have this first simple pole coming in. So a little bit past 2, or at 2 rather, we're going to start having this plus 20 dB per decade from our zero at the origin, and this negative 20 dB per decade from our simple pole. And so of course what that's going to look like is it's just going to stay constant at that point. So let me first increase this. So we have some linear 20 dB per decade increase here. So this is 20 dB per decade until we reach our frequency of 2, at which point our positive 20 dB per decade and our negative 20 dB per decade cancel out and we don't have any slope. So that is going to continue until we get to this third key frequency of 10. At 10, we now have this constant 20, which we've already accounted for, positive 20 dB per decade, negative 20 dB per decade, and now we add another negative 20 dB per decade, which means we're going to be decreasing at a net negative 20 dB per decade. And so that kicks in at a frequency of 10. So what we can do is we can draw lines up here to indicate where that frequency is. And so we stay constant until that point, at which time we begin decreasing by negative 20 dB per decade. So we get something that looks like this. So this is negative 20 dB per decade. And so I've not been very precise with where that crosses the x-axis. I'll mention here in a little bit where you can find a more accurate drawing in the textbook, but that should be crossing at 200. Okay, so that covers how to do, and so this just continues going down here. So that covers how to do our gain, our magnitude, but now let's look at our phase information. And so we're going to be doing the same idea. We're taking these 4 plots for our phase information and we're just adding them together graphically. So our phase for a constant is easy. It is just 0, so that's not contributing anything. Our 0 at the origin is giving us a constant 90-degree phase, so that's going to be pretty easy to deal with as well. And then we see that our 2 simple poles are just going to be causing a negative 45 degree per decade for each one, cutting in at 0.2 and 1 respectively. So that means up until 0.2, we're just going to have a phase angle of 90 degrees. So let's come over here and say up until 0.2, we just have 90 degrees. So now once we reach 0.2 though, we have this first simple pole cut in, and we're going to be going negative 45 degrees per decade. So we have negative 45 degrees per decade starting at this point here. So we're going something like this. Let's see, let's try to make this as accurate as possible. So if nothing else were to happen, by the time we went to 1 decade to 2, we'd have something that looks like this. But we see that this second simple pole is going to cut in another negative 45 degrees per decade starting at 1. So what we have to do is we have to come and update this and say that only goes until this point, at which point the decrease is going to happen even more rapidly. So let's update that a little bit. So let's say we're going until we get to here with that negative 45 degree per decade. So I've tried my best to sort of line that up as if it were going negative 45 degrees per decade. And let's label that for clarity. So here we have negative 45 degrees per decade. Okay. And so now we have this other negative 45 degrees per decade coming in for a net negative 90 degrees per decade. And so we're going to have that negative 90 degrees per decade until we reach 20, because 20 is where we sort of lose the contribution from the first one. So what we have then, and so let's see, so at 20, what we could see is that we should be at negative 45. So let's see if I can, again, try to draw this as accurately as possible. So from here to here, we're going to get the 2 combined. So we're going to get a negative 90 degrees per decade slope, at which point our contribution from the simple pole with a corner frequency of 2 stops contributing, and now we're back to only 1 simple pole contributing, which is this one with corner frequency at 10. So now we're back to negative 45 degrees per decade until we get to a frequency of 100. Okay, so now let's mark sort of our key points here. So we're going until we get to 100, and our final phase is going to be the negative 90. So a slightly more gradual slope there, and then we stay constant at the negative 90. So this is negative 45 degrees per decade. And so for a more complete or maybe a more accurate drawing, you can look on page 622 in the textbook. And so sort of as a check of these Bode plots, what we could always do is, and it depends on the configuration, but in this case it's easy to do for our phase, is we can sort of check our two endpoints. So for really small frequencies and really large frequencies, we can verify that it matches what we have. So in this case, we see we have for small frequencies 0 plus 90 plus 0 plus 0. So we should be at 90, which we are. For large frequencies, we have 0 plus 90 minus 90 minus 90. So we should be at negative 90 degrees, which we are as well. So hopefully that gives you a little better idea of how we can use those 7 terms in order to create a Bode plot for a transfer function which is composed of various terms.